Hello, this is a short introduction to waves. Now, waves and oscillations are often tied together. They're in the same place in the physics book, and we often talk about, well, we got these nice oscillating waves, something like that. Waves and oscillations are not the same thing, though. Here in this unit, we're mostly talking about sound. Now, is sound an oscillation? An oscillation is something that goes back and forth, like a pendulum, just back and forth in a nice regular movement, or a mass on a spring. Boing, boing, boing. So that's an oscillation. Think about sound. Does sound go back and forth? When I speak, does the sound of my voice go back to me? No. Waves. Sound is a wave. And a wave is something that travels outward. When you think about ocean waves, they travel outward. A wave is defined as a traveling disturbance in a medium. Okay, what does that mean? Traveling, okay, it's moving. Disturbance, all right, we'll have to think about what that means. Medium, well, it's just something that's traveling through. You could travel through air, you could travel through water, you could travel through a slinky. So, we can have examples of what waves would be, a traveling disturbance in a medium. The medium here is the slinky, and I'm going to go, whoop, a traveling disturbance. I disturbed one end, and you can see the wave traveling down the slinky. Now, there are two ways to make a wave on a slinky. If you have a slinky available, go get it. Hit pause, go get a slinky, and see if you can come up with a different way to make a wave on the slinky. Okay, hit pause, give it a try. All right, how's the other one? There's this one. You can see that one going up, and then as it moves down. But you can also do a wave like this. Can you see it? All right. So here are two different types of waves. We've got the whoop up, and then, the slinky's going like this, and then we've got that kind of disturbance, and then we've got this kind of disturbance, and that's moving this way. So these are two different types of waves. We can talk about this one, and this is called a transverse wave. Trans usually means across. Transportation, you're moving something across a city, across something. Here we've got longitudinal, and the way I remember this, it's along the slinky. So this way the disturbance is in this direction. Here the disturbance is in this direction. And so with a transverse wave, the disturbance is perpendicular to the direction of motion. Longitudinal, they are parallel. So when I say wave, you might think oceans, but if you like to do sporting events or concerts, you might say, hey, there's a stadium wave. So it's coming around, what do? It's coming around, and then you go, woo! Okay, transverse or longitudinal. The wave was moving this direction. What direction did you move? That way. So a wave's going that way, that's parallel. A stadium wave is a transverse wave. All right, so we can try to make different types of waves, and we can also try to do things to speed up or slow down the waves on a slinky. So again, if you have a slinky, play around for a few minutes. What can you do to make the wave, either this type or this type, go faster? What can you do to make it go faster? So hit pause, give it a try. All right, and I'm going to do a little bit here. I'm going to try that. Oh boy. And oh boy, I can't even see that longitudinal wave. No. Transverse? No. It's going so fast I can't see it. However, if I do this, yep, and now if I do this, oh boy. Let's get it mellowed out. Even slower. Yep. So for a wave on a string, and we're going to use string, slinky kind of as the same thing. A wave on a string. We have our speed. What controls the speed? Well, we need to think about what I just did, huh? So by tightening it up like this, I made it go faster. By loosening it, I made it go slower. Well, that is one piece. What would that connect to on a string? How tight the string is? That's our tension. So the speed connects to two things. It's related to the tension in the string. And does this make sense? The tension's on top. If the string is tighter, is the velocity higher? Bigger tension, bigger speed? Yeah. Fast. small tension, low speed. Okay, the other piece is not something I can change very easily on a Slinky. It's called the linear density. And what linear density is the mass per unit length. How many kilograms per meter of the string? So we can change that by thinking about a nice lightweight cotton string or a metal wire. A metal wire is going to have a lot more mass per unit length. Cotton string, not many kilograms per meter. So if we take a string and a wire, put them under the same tension, and then go flick, and watch the wave travel down, the one with the bigger mass per unit length, the metal one, the wire one, bigger mass per unit length, this is bigger, but it's in the bottom, that's going to make this slower. So things are going to go slower on the wire than in the cotton string, which is kind of interesting. So we've got this. Now we can also talk about different things with waves. We need to define a couple of things. And in order to do that, I'm going to try a picture of a regular traveling wave. This one, what we have here, we call that just a single wave pulse. So it's just that kind of one flick disturbance. But if you think about ocean waves, that's not just a single wave, unless it's a tsunami, I guess. But we think just this nice even pattern of stuff. And we can have the speed, the velocity of the wave as it's moving along, but we can also define other things. So we can define the speed or velocity. We can define the amplitude. And when you think amplitude, you think size, how big is it? Got to be careful here. The amplitude of a traveling wave is the height, but it's the height from equilibrium. So if the ocean was perfectly flat compared to up and down and up and down. So the amplitude is the height from equilibrium, that middle bit. So we got to be careful about amplitude. So if the wave is 20 centimeters tall, top to bottom, it's only 10 centimeter amplitude. We can also measure the wave length. How long is it? How far is it? What's the distance from peak to peak or trough to trough? And this is the Greek symbol lambda, and so lambda is the symbol we use for wavelength. What else can we do? Okay, the next step is harder to show on a static picture, but imagine you are on a dock watching the lake waves come by. So it's just nice, peaceful. You can hear it going foof, foof, foof. You could time how many waves go by per second, right? And that is the period. Well, actually, that's the frequency. I got to be careful here. We have frequency and period. And I just said how many waves go by per second. That is the frequency, but we could also time how many seconds it takes for one complete wave to go by, and that is the period. So you can see from these two that they are inverses of each other. Frequency is one of the period, period is one of the frequency. All right. Now for regular traveling waves, we can make a connection between three of these variables by looking at the units. Meters per second. Meters, that's a distance or a height. This is a length in meters. And now here, period. Now wave isn't a real unit, so period is just seconds. Even though we talk about it physically as how many seconds per wave. Similarly, frequency is waves per second. And so really it's 1 over seconds or hertz. All right, can you come up with a relationship between velocity and wavelength and period? Can you come up with an equation relating these three variables just by looking at the units? So give yourself a minute, hit pause if you need to. Can you come up with the relationship between these three just by looking at the units? Give that a try. It's pretty darn easy. So just look at the units of those three. What would you have to do? And if you're still struggling, start with the velocity. Velocity has to equal what? So if I start with velocity, well, that's meters per second, right? So velocity Okay, meters needs to be on top. That's my wavelength. And that'll get me a meters on top. And then I need seconds on bottom. So I could have over T. That would be meters over seconds, right? Otherwise, I could do frequency times wavelength. Meters per second equals 1 over seconds times meters. This version of it right here, velocity is frequency times wavelength. That's our big equation for the waves unit. We need that for a lot of different things. So velocity, frequency times wavelength, and that's going to be the big one. And one of the cool things, if you think about, let's do this right. Velocity is wavelength over the period. Well, if you think about the definition of velocity, it's the change in distance over change in time. Change in distance, how far did it travel, one wavelength, and how much time, the number of seconds it took to travel that distance. So this just goes back to the definition of velocity too, which is kind of cool. All right, so there's some vocabulary. Here is our big equation. The last thing I want to talk about here is just some reminders, I guess, or I don't know what to call it. I want to make you think about the visualization of these waves. This unit, we're mostly talking about sound waves, but there are a lot of different types of waves. I mean, there's ocean waves, there's the sound waves, stadium waves, and then you can also talk about light waves. So when we talk about light waves, those are waves as well. Light travels as a wave. And the cool thing is that light is part of the electromagnetic spectrum. Electromagnetic spectrum. Other things in the electromagnetic spectrum are things you've heard of. Microwaves, radio waves, gamma rays, X-rays, all these sorts of things are part of the electromagnetic spectrum. Light is actually a very small part of it, visual light. We are taking up this much of a spectrum, this big, for the visible light, what we can see. And the cool thing about everything on the electromagnetic spectrum, the speed of an electromagnetic wave is the speed of light, which is 3 times 10 to the 8 meters per second. That's big. 3 with 8 zeros after it. That's how fast light travels in 1 second. It's the fastest thing we know of. All right, so with light and sound, I want you to keep in mind when you visualize it, does light travel one-dimensionally? No. That would be like a wave on a string. Is light a width that's all traveling like this? No, that's kind of the ocean waves. If you think about ocean waves, so a wave on a string is just like this, just a single line. And ocean waves, if we do a top-down view of ocean waves, we might see the peaks. If I draw just the peaks, we might see them moving, these nice lines, but moving down. This is a 2-dimensional wave. Light and sound are 3-dimensional waves because you can hear me even if you're behind me, right? You can see this light from anywhere that where you can see the bulb. So we have 3-dimensional waves for light and sound. So for a string, well, that's 1-dimensional. The ocean waves are 2-dimensional, and then light and sound, oh, this is really squeaky, sorry, are 3-dimensional waves. And that is going to be important for some of the other things that we end up doing. All right, so this is a short introduction to waves. Some vocabulary, our big wave equation, and some interesting stuff to keep in mind about how many dimensions we're working in. And for sound, 3D, because you can hear me anywhere around me. So that's what we've got. Good job for listening.